Welcome. Today I'm going to do the 2023 linear algebra exam, and I'm going to do it in, I hope, about an hour, but we'll see. So you have 90 minutes to do a similar exam. A pocket calculator or graphics calculator is permitted. No mobiles or laptops, and you can bring in your notes. Okay, let's get started. Consider the vectors u and v in 2 space. Calculate w, which is 2u minus 3v. So let's go ahead and do that. So 2u minus 3v, this is part A, is equal to 2 times minus 2 minus 3 minus 3 times 1, 4, which is equal to minus 4 minus 6 plus minus 3 minus 12. And so we get the sum of these is minus 7 minus 18. Okay, part B. Explain whether w is an element of span of u and v. Yes, of course it is, because we have w is equal to 2u minus 3v. And remember that span of uv is the set of all linear combinations of u and v. Let's say that, though. Okay, so now part C. Determine whether u and v are orthogonal. Well, what we need to do is take their dot product. And so we get minus 2 minus 12, which is minus 14, and notably that's non-zero. So u and v are not orthogonal. They're not perpendicular. Okay, let's move on to question 2. Consider the vectors u, v, and w in the vector space R2. Write w as a linear combination of u and v. Now, sometimes you can guess, and it's possibly worthwhile spending a few seconds trying to guess. All right, so if I add u plus 2v, I get plus 5 and minus 1. So I think I want the opposite of that. So just guessing, what do we say? U plus 2v gives us the opposite of w. So minus u minus 2v is minus 1, 1, minus 2, minus 1. Which is, minus 2 that. Okay, which is minus 5, and then we have plus 2 minus 1 is plus 1. But if you weren't able to guess, if you were not able to guess, then what you would do, so alternatively, you would say, suppose alpha u plus beta v equals w. And so if we have this, then we can express this as 1, 2, 1, minus 1 times alpha beta equal to minus 5, 1. And then solve this system for alpha and beta either by row reduction or taking the inverse of this matrix. Let's take the inverse of the matrix. So if A is equal to 1, 2, 1, minus 1, then A inverse is equal to 1 on the determinant. So we've got determinant minus 3. And then we swap these diagonal elements and put minus signs on the off diagonal elements. And this is our inverse. And so alpha beta is equal to A inverse times W. So minus 1 on 3, minus 1, minus 2, minus 1, 1, multiplied by minus 5, 1, which gives us, so 5 minus 2 is 3, and then minus 1 times minus 5 is 5, plus 1 times 1 is 6. Okay, and so this simplifies to be minus 1 minus 2. All right, which gives us alpha and beta. And again, we would see then that W is equal to minus U minus 2V. Okay, so that's part A done. Are the vectors U, V, and W linearly independent? Well, no, because this equation right here shows, or sorry, this one right here shows you that, or this one is here, shows you that they are dependent. And so let's write that dependence and say we have U plus 2V plus W is the 0 vector. And since the coefficients 1, 2, and 1 are not all 0, what we get then is that the three vectors are linearly dependent. And hence not linearly independent. Okay, now let's do part C. Except I think we're going to need more paper, so do we have another page? No. So grab a page. You might want to grab an extra page. Okay, part C, show that, I guess I'll do this. Show that the span of U, V, and W is R2. Okay, so let's write a simpler spanning set than this, since we know that these three vectors are linearly dependent. So we'll say, since we have W equal to minus U minus 2V. I hope that's what it was. Let's have a look. Yes. Okay, so since we have that, W is in the span of U and V. And so what we learn from this is that the span of U, V, and W is equal to the span of just U and V. Okay, now, are U and V linearly independent? Yes, they are, because they are not multiples of one another. Have a look. The vectors U and V form a basis for the span of U, V, and W. So we can't go any lower in our spanning set than just U and V, in numbers anyway. Okay, so now let's say that clearly span of U and V is a subset or equal to R2, since every linear combination of U and V is into space. Conversely, to show that R2 is a subset or equal to the span of U and V, we must show that every element of R2 is a linear combination of U and V. So take some vector, say Z equal to PQ in 2 space, where P and Q are real numbers, and show that we can always solve for alpha and beta in the real numbers such that Z is equal to alpha U plus beta V, right? Because if we can always solve for alpha and beta satisfying this, then we're showing that irrespective of what the value of the vector Z is in R2, you can always find or always express Z as a linear combination of U and V, and hence it would be in span of U and V. Okay, so let's go ahead and show that we can always solve this. So in other words, if we have alpha U plus beta V equals Z, then we can write this as 1, 1, 2 minus 1 times alpha beta is equal to PQ. And whether or not we can solve this depends on whether this matrix on the left, this 2 by 2 matrix, is invertible. So we can solve for alpha and beta if and only if the matrix A is invertible. Okay, so let's take its determinant. So we have 1 times minus 1 is minus 1, and then minus 2 times 1 is minus 2. So we have minus 3 as our determinant. This determinant is non-zero, so A inverse exists. And we have alpha beta equals A inverse PQ, right? So whatever P and Q are, we can always get a corresponding alpha and beta. Okay, so this shows then that 2 space is a subset or equal to span of U and V. So let's say we have shown that span of U and V is a subset or equal to R2, and in the latter part, the other way around as well. So they are equal. And remember, span of U and V is span of UVW. Okay. All right, so now let's have a look at part D. What is the dimension of the vector space span of U, V, and W? Well, it's obviously 2, because remember we found that this is a basis for that span. Okay, so part D, since UV is a basis for span of UVW, the dimension of the span of UV and W is the number of elements in this basis, which is 2. Okay, let's move on to the next page. Question 3. Let V be the vector space over R consisting of all polynomials in the variable x with real coefficients. Determine whether the polynomials f, g, and h are linearly independent. Okay, so we make the usual setup. We say suppose alpha f plus beta g plus gamma h is the 0 vector. And so if you were to expand these, and I guess let's go ahead and do that. So we would get then alpha x squared plus 3 alpha minus beta x squared plus beta x plus 2 beta plus gamma x squared minus 2 gamma x minus 7 gamma equals 0. Okay, so let's collect the like terms. So we have alpha minus beta plus gamma all times x squared. And then the coefficients of x, we have beta minus 2 gamma times x. And then we have 3 alpha plus 2 beta minus 7 gamma. All of this is 0. All right, so now there is a corresponding system of equations. So this is 0. This is 0. As in, if they are linearly independent, then all of these... No, hang on. Okay, so no, all of the coefficients must be 0 because we have 0 on the right-hand side. Sorry. Okay, so back to this. 3 alpha plus 2 beta minus 7 gamma is 0. And so now we can write this as a matrix equation. Okay, and so what we want to know now is when we solve for alpha, beta, gamma, are we forced to get 0, 0, 0? If this matrix is invertible, then we would be forced to get 0, 0, 0. If it's not invertible, then it would be linearly dependent. But if we just use the determinant of this matrix to decide that, then we don't get the actual coefficients. And it's nice to get the coefficients. So let's go ahead and take the row-reduced echelon form of the augmented matrix, concatenating this matrix with the 0 matrix there. So the augmented matrix is 1, minus 1, 1, 0, 1, minus 2, 3, 2, minus 7, and we have over here 0, 0, 0. Okay, so let's do some row reduction on this. I will multiply the top row by 3. And the reason to do that is so that I can subtract row 1 from row 3 and replace row 3 with that, which we'll do now. So 3 minus 3 is 0. 2 minus minus 3 is 5. Minus 7 minus 3 is minus 10. And 0 minus 0 is 0. Okay, now let's multiply row 1 by 1/3 of row 1 and get 1 minus 1, 1, 0. Continuing, let's multiply row 3 by 1/5 of row 3. And let's replace row 1 with row 1 plus row 2. Okay, now you can see that row 1 and row 2 are multiples of one another, and so I can replace row 3 with row 3 minus row 2, and we get a row of zeros. And this is in row reduced echelon form. Okay, so how do we interpret this now? So now we can go back to the equations and say that this says alpha minus gamma is 0 and beta minus 2 gamma is 0. And so what this says then is alpha is equal to gamma, beta is equal to 2 gamma, and gamma is equal to gamma. And so now if we choose a value for gamma, so let's say choosing gamma equals 1, we have alpha is 1, beta is 2, and gamma is 1. And so this gives us the linear combination that gives us 0. So we have f of x plus 2g of x plus h of x equals 0. And so no, these vectors these polynomials are not linearly independent, they are linearly dependent. Okay, let's move on to page 4. Okay, so we have a matrix. Calculate a basis for the null space of A and a basis for the column space of A. So what we want to do with this is row reduce this matrix. Hang on, did I just do this in the last question? Is this the same one? Let's check. Yeah, it is. So we've already got this. Okay. So we have the row reduced echelon form here. And we'll just say from question 3. Okay, so now it just remains to interpret what the null space and the column space are. So let's have a look at this. Pivots of the row reduced echelon form of A occur in columns 1 and 2. So circling these here and here, so columns 1 and 2. So, excuse me, extracting columns 1 and 2 from A, we see that the column space of A is equal to the span of 103 minus 112. So we have a basis, because these two vectors are linearly independent, so this is the basis for the column space of A. Okay, so now for the kernel, so let's say let x, y, z be an element of the null space of A. So then what we would have is 1, 0, minus 1, 0, 1, minus 2, 0, 0, 0 times x, y, z equal to 0, 0, 0, given that this vector is in the null space of A. It's also in the null space of the row reduced echelon form of A. And so expanding this out, we have x minus z equals 0, y minus 2z equals 0, and so that gives us x, y, z is 1 times z, so 1, and then 2 times z, taking the 2z over to the right hand side, and then z is equal to z, so 1 times z for z. Okay, great. So now we have a basis for the null space. 1, 2, 1 is a basis for the null space of A. Okay, now for part B, the rank of A is the dimension of the column space, which is 2, because this has two vectors in it, and the nullity of A is the dimension of the null space, which is 1. Also notice that 2 plus 1 equals 3. All right, let's move on to question 3. Now consider the linear map, uppercase F sending R3 to R3, given by F of XYZ is A times XYZ. Calculate the dimension of the image and the dimension of the kernel of F. Well, we already have that because the image of F is the column space of A. So let's write this down. So the dimension of the image of F is equal to the rank of A, which is 2, and likewise the kernel of F is the null space of A, and so the dimension of the kernel of F is equal to the nullity of A, which is 1. Okay, part D, show that the image of F is a subspace of R3. Well, I don't think that we need to say a lot here. Okay, so note, let XYZ Well, maybe I should have chosen other letters. So let's go uppercase X, Y, and Z. Be an element of the image of F. Then we know that X, Y, Z is a linear combination of the columns that we got earlier, which would have been columns 1 and 2 of the matrix A. Okay, so it's a linear combination of these two vectors. And so we can see then that the image of F is a subset or equal to span of those two vectors. So let's call this W. Now clearly the 0 vector is in W. And hang on, these are equal, right? So let's just put equal. And so this is a subset of our 3 here. Okay, so 0 vector is in W. W is closed under addition because if we take a linear combination of these two vectors and another linear combination of those two vectors and add them together, we will get a linear combination of the two vectors. Since if alpha 1 times 103 plus beta 1 times minus 1, 1, 2 is in W, and alpha 2, 103 plus beta 2 minus 1, 1, 2 is in W, then the sum of these two things is in W. Okay, and similarly, W is closed under scalar multiplication. Since if we have alpha 103 plus beta times minus 1, 1, 2 in W, and then we multiply by some scalar, K times this, is also in W because it's a linear combination of those two vectors. Okay, so W is a subspace of R3. Okay, let's move on to the next page. And final question. Let A be the matrix minus 7, 4, minus 12, 7. Calculate the eigenvalues and eigenvectors of A. Okay, so let's take the trace of the matrix A. which is the sum of the diagonal elements, so minus 7 plus 7, which is 0. And the determinant of A is minus 49 minus minus 48, which is plus 48, which is minus 1. And so the characteristic equation is lambda squared minus 0 times lambda minus 1, which simplifies to lambda squared minus 1. And we can factorize this easily. And this is equal to 0. Okay, so let's say lambda 1 is 1 and lambda 2 is minus 1. So we have our eigenvalues. Okay, so now let's find the eigenvectors of A. So A minus lambda 1I is equal to minus 7 minus 1, 4 minus 12, 7 minus 1, which is equal to minus 8, 4, minus 12, 6. And this is row equivalent to 2 minus 1, 0, 0. And if you like to have this in the row reduced echelon form, you can. So this final matrix here is in row reduced echelon form. Okay, so we can read off just from this one the eigenvector x1. And so I'm swapping the elements. I'm writing this one first, the second one first, and putting a minus sign on one of them. I choose the one that already has a minus sign because it makes it plus, and I like plus. Okay, so here's an eigenvector, or any multiple of that would be fine. And this corresponds to lambda 1. Now let's do the eigenvector for lambda 2. So we have minus 7 minus minus 1, 4 minus 12, 7 minus minus 1. And so we get minus 6, 4, and minus 12, 6. Okay, so this is row equivalent to 3 minus 2, 0, 0. And if you like the row reduced echelon form, it's 1 minus 2/3, 0, 0. Okay, so I'm going to look at this matrix and write down x2, our second eigenvector, is 2, 3. So what I'm doing is I'm writing the second one first and the first one second and putting a minus sign on the minus 2. Okay, great. So we are finished with part A. So x1 and x2 are the eigenvectors of A. So part B, so we have A equals P. Now P consists of just concatenating x1 and x2. So 1, 2, 2, 3. And then D is the diagonal matrix consisting of lambda 1, lambda 2 respectively. 1, minus 1 down the diagonal and zeros elsewhere. And now P inverse is just the inverse of this matrix. So let's calculate the determinant of it. It's 3 minus 4 is minus 1. So we have 1 over minus 1, and then we swap our diagonal elements and put minus signs on the off diagonal elements. Now let's simplify this, because that fraction here is just minus 1, so we can put that minus 1 inside, and it's still relatively tidy. So we have 1, 2, 2, 3, 1, 0, 0, minus 1, and minus 3, 2, 2, minus 1. Okay, so this is P, D, P inverse. And this is our diagonal decomposition of A. So we are done with part B. Okay, now part C, which I'm going to fit here in this little space because it doesn't take much. A to the power of 4 is equal to P d to the power of 4 P inverse. And so d to the power of 4, we just take the fourth power of these diagonal elements in the diagonal matrix. So we've got 1, 2, 2, 3, and then the fourth power of these is just the identity matrix. So we get minus identity times this is minus 3, 2, 2, minus 1. And if we expand this out, this is supposed to give us the identity matrix here, because this is P inverse and this is P. And so we've got 1, 0, 0, 1 for A to the power of 4. Okay, so A to the power of 100 is equal to A to the power of 4 all to the power of 25, which is the identity matrix to the power of 25, and that has to be the identity matrix. Okay, and we are finished. Thanks.